All right. So to begin this lab, we'll run, as I said, first the principal component analysis using the notebook that we have prepared for this class. And then we'll move to GeoDa to run, again, the principal component analysis, but straight away from GeoDa so we can better visualize the results. I'll skip everything about the imports, the environment, the Conda environment that I'm using here and all, because we've discussed this already on our first class. So one thing that is important is that, as I said, we will use PCA from Scikit-learn, but first we'll just run it by hand using NumPy and SciPy to make sure that actually Scikit-learns as well for the scalar to make sure we understand exactly what is going on behind the scenes. So as you can see here, the data that we'll be using is the query data. So I'll just load it. And here we have the description of all variables. As Luke said at the beginning of this class, we need to pay attention when using these data because crimes against persons, crimes against property, infants and suicides, they are flipped around from what we're used to, right? So the higher the values for these variables, the lower is the ratio of crimes and the lower is the ratio of births outside of the marriage and the lower is the ratio of suicides. Just that the way the author created these variables was dividing the population by the actual number of events. So it was an inverse of what we're used to. So the first thing we need to do to run the PCA, again, let's think about the objective of this method. So we want to get the correlation of the variables, that the original variables. So the more correlated they are, the easier it will be to compress the variance of them into new components, into new variables. So the first thing we'll need is to assess exactly the correlation that we have between our variables, right? So what we are doing in this cell is just selecting the variables of interest. So we're focusing only on these 6 variables that we have. And then after selecting them, I'm just creating this correlation matrix so we can see how they correlate to each other. As Luke already highlighted, not well enough, right? So the correlation is not very high. So we have several variables that are that show very small correlation between each other. So we can already expect that the variance that we will have with the principal components will not be that high. So we will need several components in order to achieve a high degree of explained variance. But let's begin doing then the principal component analysis by hand. So Luke mentioned that there are 2 ways in GeoDa to do that. So we can either use the eigenvalues or we can do the singular value decomposition. So here we'll use the eigenvalues, so the more classic way to run the PCA. So to begin with that, the first thing we do is to standardize our variables, as I said. So the variables now will have mean of 0 and variance of 1. So when we standardize them, we can see that. So the mean of all the variables is 0, right? Roughly 0. And the standard deviation is, again, roughly 1. So that's the result that we get out of the standardization. So once we had, yeah.
One thing that I didn't realize until I was doing the notebook for k-means and I saw that the results were different from GeoDa, is that the standard scalar that we use here computes the variance by dividing by n, the number of observations. GeoDa standardizes by dividing by n-1, which is the degrees of freedom. So in some, but not in standard scalar, you can adjust this by setting the degrees of freedom up argument in SciPy or Scikit-learn, but not in standard scalar. So if you want to replicate exactly the numerical values of GeoDa, you need to rescale the results of standard scale. So again, I didn't notice this at this stage, but you'll see it is when we deal with the clustering, there'll be additional explanation. So if you would do this in GeoDa, you might not get exactly the same results because the scaling, the standardization is different.
Okay. So with the variables now standardized, we can just create our correlation matrix. So now that they are standardized, we can just do x prime x and then divide it by here the number of variables, right? The number of observations. So x prime x divided by n, and what we get here is the correlation matrix. Alternatively, you could just go ahead and use data PCA, the object that we have with our variables, and use the function .core. You would get exactly the same result, right? So, but again, in the spirit of doing things by hand, that's what we're doing here. Just doing x prime x divided by the number of observations here, by p. So we get our correlation matrix. The same thing that we had before when we actually checked the correlation. So let's just move forward. Next step then is working with the eigenvalues. So actually getting our correlation matrix and computing its eigenvalues and eigenvectors and corresponding eigenvectors. The idea here is that the eigenvalues will be just, by matrix algebra transformation, the eigenvalues will represent the variance for the components, and the eigenvectors will represent the loadings, right? There will be the loadings for each of our components. So if we think about it, by looking at the eigenvalues, we get how principal component analysis is always preserving the total variance that we have in our data. Because if you think again of the correlation matrix, the trace of this correlation matrix, or the sum of the main diagonal, right? It's the total sum of the variance of our data, correct? Since we have standardized data, in this case, it will be the number of variables, right? K. But anyway, so the trace, or the sum of the main diagonal, will be the total variance. The sum of all the eigenvalues that we have in a matrix is also the same thing, right? It equals to the trace. So it equals the total variance that we have. And since the eigenvalues are the individual variances of the principal components, we know that the sum of the variances of the principal components, again, will equal the total sum of the variance that we have, right? Again, all of that because sum of eigenvalues equals trace of the matrix. So in this case, it's a correlation matrix equals the total variance that we have in our system, our original system. So PCA will preserve the variance. It will just, again, kind of rearrange it in a way to compress as much as possible in the first components, because we will order the components as such, right? We will order the components in a way that the ones with the greater variance, so the greater eigenvalues, will be the first ones. All right, so what this cell is doing is pretty much just showing us eigenvalues and eigenvectors, right? So we get the eigenvalues and vectors, and this cell is printing them out, and then printing the first PCA, the vector for the first one, and that's it, right? And then it's just labeling things out so we get a better labeling of this result. Oops, I forgot to run, as always, the cells above. Maybe I shouldn't be running them, but anyway. Okay, so what we get here is eigenvalues, 2.14, 1.20, 1.10, 0.34, and then it goes. So from this result, if we were to apply the Kaiser criterion, we know already just from the first result that we got in this application that we would retain only the first three components, right? The other three we would be able to discard. So again, a significant decrease in the dimensionality of this data. Out of 3 variables, we would keep only, out of 6, we would keep only 3. Not as good as we would like if we had a better correlated data, but anyway, this is the result that we get. And the eigenvectors are all here. So the first eigenvalue is the greatest one. Since it's the greatest one, we know that the first eigenvector will be the loadings for the first component, right? So he's just highlighting the first principal component loadings.
This is not sorted. It looks like it's sorted. but it's
Oh,
not. If you
yeah,
look at
here.
the last 3 elements.
So we were
Not
lucky that the
lucky,
first, yeah, we did not use the sort function, right, from NumPy to make sure that we would get the right result. But we were lucky that the first 3 were indeed the ones they ordered, right, as we would want them to be. But it shows that the last 3 are not. So actually, what would be the component 4 here? So the 4th principal component is the column number 4, or the 5th column that we have in our data, right? Because of the ordering. So this guy here would have to be the last principal component, right? Because it's the smallest variance. Okay, so this is showing these loadings just, in a better way. So again, it's the result we discussed already. So we can tell that in the first component, what we get is that crimes against property, infants outside of the marriage, and suicides have a strong loading in this first component with a negative sign. So given the way the variables are constructed, we know that more crime will result in a greater value for component 1. Okay? Because more crime means a small value for this variable, and then a small value for this variable, since it's negative, means greater value for component 1. Okay? So more crime, we have a higher value for component 1. More infants outside the marriage, more like a higher value for component 1. More suicides, higher value for component 1. Again, because the variables have this inverted interpretation due to the way they were created. As Luke said, this is definitely not the best data set to interpret this, but let's go to literacy, because then the interpretation is straight away. It's not an inverted variable in the way it was constructed. So what we know is that more military that know how to read and write also means a higher value for component 1. All good? Okay? So we can tell now only from this, only from the eigenvectors, we can already try, if possible, to label PC1 if we can, or at least understand what it represents, right? So higher values of PC1 will represent higher literacy, and low values for the other variables that have negative signs. And a low variable for PC1 will represent low literacy and high values for the other variables that have large loadings and negative signs. If we go to component 2, so PC2, our column label as 1 here, what we can see is that the variables that were kind of neglected from the first component will have higher loadings here, like greater loadings here. So crime against properties and donations had very small loadings on the first component. So now they still have a lot of variance unexplained by the principal component, so they will tend to load more on the second one, as it happens here. So what we see is that a low value for these variable, crimes against properties, imply a higher value for component 2, and a low value for donations implies a higher value for component 2 as well. Then running quite behind, but still maybe significant, maybe not, we have suicides again with a loading of 0.35, showing that a high value for this variable implies a high value for the second component as well. But it's running quite behind of the other two. So maybe we could just focus on the other two when trying to label this component if, again, we were to do so. And if we were to label it, as I told you, I used large language models. So let me just go back to see what would be the label that it recommended. I forgot, but it was something like compassion and crime. See, because again, it's about donations and crimes against properties. It's quite poetic, right? So let's move forward. We're still trying just to do things by hand, and we stopped on the main result, I think, of depending on what you want to do, but that is the loadings, right? Because the loadings allow you to be able to interpret what you get from the components, right? So if you do not pay attention to the loadings, you cannot really tell what you're measuring with the components that you're creating. So making sure that you can understand what the loadings are showing you is really, really important. In the next cell, then, we pay more attention to the variance that is explained by each of these components, right? We already know the variance of each of them because that's just the eigenvalues. But here, we're just trying to interpret better what we have about variance. So total variance is 6, because again, we have 6 variables and they were standardized. So the variance of each of them is 1. Again, total variance 6. And the share of total variance that we get in each component then is that we know from here that the first component has 36% of the variance and the second component 20% of the variance. So if we use 2 components, we would have only 56% of the variance. Not good, right? So maybe we think about adding a third one, and with the third one, we add more 18%. So it gets us to 56 plus 18, 74, right? So I don't know, still debatable, right? 3/4 of the variance may be okay, depending on what you're doing and how strict you are with your application. We did not compute the cumulative sum, but then of course it's easy for you to do it. So you can tell exactly when it reaches like 3/4, quarters, or 95%, or as much as you want.
Yeah, but Pedro, to do it right, you would have to sort them first.
True. Yeah, here you can see that again. We have the 11% on the second to the last, and then 9%, and then 5% here. So to do the cumulative right, you would have to sort them first. Here, of course, it doesn't really matter because we're looking at the individual variance, but the cumulative, it's important. It is important to sort it first. And that is it. So, I mean, what are we doing with the PCA again? We're just getting the correlation matrix, and from the correlation matrix, we're computing eigenvalues and eigenvectors. And then from the properties of eigenvalues and eigenvectors, we know that we can combine our original variables using a weighting scheme that is based on the eigenvector of this correlation matrix. And the variance that we'll have out of this weighting scheme will be exactly in total the same variance that we had before from our original data. So we're creating this weighting scheme that is combining our original variables into new variables, but using their correlation to get as much variance as possible in the first new variables that we're creating, the first components. By doing so, we are reorganizing the whole variance, the whole variability that we have in our original system. And then what we can do, depending again on our objective and something we'll choose, we can just disregard the new variables that have very small variance. So that represent very little of the whole variability that we have in our data. And if they represent very little, maybe they can just be discarded without much harm. Okay, so again, by using principal components, we can focus on what is more important by compressing the variability in fewer variables. And then depending on our research decisions, we can just discard the others. And by doing so, decrease the dimensionality of our data. Right. So in this case, maybe we would focus only on 2 or 3 components or 2 or 3 variables, new variables, instead of all the original ones. All right. So this is it. Now let's just do it in the way Scikit-learn will help us doing it. So we're not actually just computing ourselves eigenvalues and eigenvectors. We'll just redo the whole thing. And you can see that everything that we did above, we can do with this single line pretty much, right? So basically, we're just repeating it here for conciseness. So if you just want to run this cell, it will do everything. But anyway, so here we're reading the data again. We already have that. We are selecting only the variables of interest. We already did that as well. And we're standardizing our variables. So here we can use the PCA function from Scikit-learn and fit that function to our variables. Okay? So by running this, we get many attributes to this new object that we have out of the PCA. One of the objects that we have, or the attribute, sorry, is this components attribute. So when we check it, we will get the loadings row by row. So again, the same loadings that we had before. So we can know again which variables are important or not, how to interpret this first component and all of that. The attribute explained variance will show us the eigenvalues that we have. So here, basically, we have the eigenvector. Here we have the eigenvalues that we get from our analysis. So again, from here, we can say that maybe from the Kaiser criterion, we would select the first three components. If that is enough or not, we can look at the explained variance ratio. And from the explained variance ratio, we can see that PCA function will sort the components for us, right? So they are sorted here. So we can just see again how much variance we want to retain, how much variance we think we can discard. So in order to favor simplicity over like comprehensiveness of the variability, so we can choose all from here. To support us with the decision of how many components to retain, so how much variance to choose for our analysis, we can plot the scree plot, right? So this whole matplotlib function here, functions, if we run this cell, we'll be able to create this scree plot, which is basically showing where we have more or less explained variance according to more or less components. So as Luke said, this is pretty much to help us like solve this trade-off. How much more complexity do we want to add to our analysis in order to get more representativeness for our variance, right? To add more variance to the data that we will actually analyze, or how much more we value simplicity, and then we are willing to discard more variance and just focus on fewer components. So as Luke said, based on the slope here, we can take this decision. So if we really value simplicity, maybe we would stay, I don't know, with three components because we have like high variance for them and still few components. But if we want to add more variance and then add more complexity, we could likely go to, I don't know, 5 components. That wouldn't make sense at all. But from the graph, this would be what I would do. Does it make sense how to interpret this and how to choose where to stop? The thing is, basically, if you, of course, one, if you really want just an index and you think you have enough variance, you stick with one. Okay, that's your decision, right? But if you're considering keeping 2 components, you look at the explained variance you have for the second one, and it's about 20-ish, right? If we compare that to the third, it's pretty much 20-ish as well. So you don't really have much arguments to select only 2, since the second one represents pretty much the same amount of variance that the third one represents. So unless you try to use an argument of visualizing graphs, and then 2D would be as much as you can do with simplicity, you don't have many arguments to choose 2 only. So it's either 1 or 3 at this beginning. Okay? Because then, again, between 2 and 3, they pretty much show the same amount of variance, of variability. Then you go to 4. 4 shows significantly less. So that's a good justification, a good reason to discard 4th and everything else that comes after it. Okay? But if you decide, again, for any reason, I want to keep 4, then the same argument that we did for 2 and 3 is applied here. If you want to keep 4, you should keep 5 as well, because, again, it's pretty much the same variance. So there aren't that many arguments to discard 5 if you're keeping 4. Is the interpretation good? Okay. But of course, then with 6, you have your original variable, so you shouldn't be running PCA at all, right? If you're retaining pretty much all your principal components, you're not gaining anything out of the analysis. You're just making it harder for yourself to have to label these components in order to interpret them, and then it will just create more confusion than it will help. We can also visualize the results of this PCA by plotting the biplot. So this is what we have here. And what the biplot will do, it's basically 2 layers of graphs on the same one. So the first layer is this point graph. The point graph is showing our observations. So here we can tell what is, like, where each of our observations stand when we check their values for principal component 1 and for principal component 2. So for example, if we wanted to highlight any of the regions here, I don't know, let's say region 1, 2, 3, and 4, we could label them in this graph and show, oh, this is a region that has a high value for PC1, but a low value for PC2. So if PC1 is the whole knowledge and vice thing, they have a lot of knowledge and vice, and they also don't have compassion and what was the other thing? Anyway, compassion and civility or whatever, because the other variable is crime, right? So can you see? So if you were to label if we were to label these points, we could say, yeah, this is a region with high value for PC1, low value for PC2. These are regions that are basically around the average of the components that we just created. So basically around the average of the variables that the original variables that we have. And so this biplot, one useful way, I think, to interpret it is to divide it in quadrants. So the first quadrant that we have here is showing observations that have greater than average values for PC1 and greater than average values for PC2. So the first quadrant is observations with high values for both. And if you can't label them, or if you can't remember what the components show, the second layer of the graph will help you. So these points, if we check the vector here that we have for infants, we know that these 2 points show the largest value for this variable. Given its nature, we can tell that these are the 2 regions that have the lowest values of suicides per population, right? But in this case, it's population per suicide. So they have the highest value for this. So these points in the second quadrant, they show high values for PC2, low values for PC1. Again, let's just check the vectors. So we know that quadrant 2 shows observations with low values for the variable suicides, low values for the variable crimes against properties, and high values for donations, crimes against persons, and all of that, right? Again, just look at the vectors. So all observations that fall in quadrant number 2, they, again, will show low values for these 2 variables and high values for the ones that are in that direction. I mean, I won't be repeating myself all the way, so it's the same thing applies for quadrant number 3 and quadrant number 4. So you can tell from the vectors that you get, like exactly what these represent. The vectors that we have for the variables, if you look again how they are shown here, they represent exactly their loadings. So we know that donations and crime against persons have a high value of loading for PC2 and pretty much 0 loading for PC1 because they are like pretty much on the direction of 0 only for PC1 and they have high values for PC2.
So if you remember the graph from the slides, it was exactly the same thing. That vector was actually flipped to the other side because of the different sides. So it was in the same direction, it was going up and a little bit off of the vertical axis, but it was to the left of the middle axis. If you look at the slide, well, it's not worth it, but you can look at it, you see it's the exact same relative proportions, but it's aimed in the other direction because the signs are different for PC2. There you go.
Okay.
It's the same thing. Donations and crime against persons are going up big time for PC2, but very little for PC1. But the sign for PC1 is negative, whereas in the notebook, it's positive.
Okay. So again, you can kind of mirror this biplot in any direction you want. As long as you do it for all the loadings, you'll still, because remember the relative proportion of the loadings is what matters. So you can just flip them all, the signs of all the loadings from any of the components, as long as you do with them all. You can't just choose, oh, I'll just flip for this variable, no, right? Then you're changing the relative weights. So if you just flip everyone, then it's the same. All you'll have to do is adjust your interpretation, right? Because if you flip it, then if what was high before would be low now, what was low before will be high now. Okay. All right, so this is the biplot. So it shows a lot. It pretty much resumes. If we had here and this is something, of course, it's easy to add. I just didn't think of it. But if we added here to PC1, the explained variance, and PC2, like into the label of the axis, the explained variance, we would basically have all of the results of the PCA in the same graph, right? The biplot is good enough to be able to show us in a visual way almost everything that matters from the PCA, the results that we get from the PCA. And then, of course, we can go ahead and spatialize these results and try to get more spatial insights out of it. The first approach we do here is just plotting the component one as a box map. So by doing so, the hinge that I think we did here was, it's 1.5, the default, right? 1.5, yeah. So the default of 1.5. So what we have here is that using that hinge, we can see, and here you've seen that I've labeled this component as Morrow statistics, period. And again, my choice, it's just what I did, but maybe it's not the best label. You could use something else. Yes. The biplot?
The context of replication of PCA, so basically where the first two components don't really explain that much of the variance, and it's more like just how would the plot move in terms of the red vectors?
Good question. It's a biplot, so you always do it in 2 dimensions. So what you could do is, let's say you keep 3 components. So what you could do is plot 1 against 2, 1 against 3, 2 against 3, just to see what happens. But then it wouldn't help you that much, right? So remember that the biplot is just showing you exactly what you had already before from the tables. So in that case, if you're using more than 2 dimensions, maybe it won't really be helpful to use the biplot as an analysis tool, because you want to be able to see exactly principal component 1, 2, and 3, right? At least that's what I would do. But if you do want to do the graphical analysis, you do it 2 by 2. So you do 1 against 2, 1 against 3, 2 against 3. So you can actually visualize all the combinations that you have or the errors. So what you would have is that, let's say I'm having the third component as well. So imagine here on the side of this graph, something that is plotting PC1 and PC3, right? The x, like the vectors that you get for the variables, they would go exactly in the same place for PC1. But of course, they would change because their directions on the y-axis would change according to their loadings on PC3, right? Every dot that you have here would remain with the same value for PC1. But again, they would change on the graph, their positions, because they would match the value that they have for principal component 3. Yeah, you could do maybe a 3D graph, but yeah, because there are already so many dimensions in this biplot that if you like dimensions in the sense of you see the loadings, you see the scores, you see, you know, how the observations are distributed across them, that if you add a third dimension, and so you would have like a triplot, right? A triplot, at least for me, that would not work. But technically, of course, you could do that. Does it make sense?
The other thing in response to your question is that the length of the red lines will change. So depending on the dimension that you're looking at, if the loading of that dimension is much smaller, they will become shorter.
The shadow on x-axis should stay the same, and then
the x-axis stays the same, but the one for the other axis will change and could be further or closer.
Yeah. One thing I didn't show, and now that Luke mentioned, maybe it's important to explain to you and highlight that, is that this biplot, we usually cheat when representing it because we want to make the loadings visible, right? So we rescale those loadings. Remember, when they are computed, this vector size is 1. But you can see here that, I mean, this is not going to something that is much smaller than 1, right? It's because I'm rescaling them so we can actually see them on the plot. Otherwise, they would be very small. So the lines would be very small. So here somewhere, I think, yeah, somewhere around here, I'm rescaling. Maybe it's this constant, I don't know. But I'm rescaling the loading so we're actually able to see the lines in this graph. Okay? All right, so from the biplot, I mean, if you're able to label these better, so let's say you call this knowledge and vice, or you call it any of the other ChatGPT or any AI model that you're using, options that you get. So the map will be more meaningful in the sense that you'll be able to tell that these are the places with higher moral statistics. Again, thinking about what is moral and not from the 19th century convention that the author used in his paper. And we would know just from this map that this northern part of France would have less values or less morals in that sense in that time. Okay, so we would be able again to compress all this information on moral statistics in a single map and already identify the regions that concentrated. One more thing we can do is by using PyGeoda, we can use the local neighbor match map or test, sorry, to see, and also the Moranzai, sorry, I said it wrong. We can use the Moranzai as we did in the slides, and using the Moranzai, we can see exactly how these regions cluster within France. So as I just showed on the biplot, here we're just highlighting the regions that are more important with statistical significance. And as I said, up to this point, we were not saying anything about the statistical significance, and now we are, right? So what we know is that these blue areas, they concentrate regions with low values of moral statistics, and these red areas, they concentrate regions with high values of moral statistics. So you have units with high values surrounded by other units also with high values, and in the blue is the opposite. And here we have an outlier region that shows low value for these morals and within a neighborhood of high values for the morals. All right. So this is it for the notebook. Let's just go to GeoDa. So I'll show you how you can use GeoDa to pretty much run the same analysis with the additional possibility of using the linking and brushing. So you can actually visualize different graphics and highlight observations in all of them. Let me just clean up a little bit my desktop so I can share my full screen. And then I can open GeoDa.
By the way, while we're on the topic of GeoDa, there is a new release. If you remember, we had some issues with the variables included the first week. Remember the total population? Some of you had it, some of you didn't. So the latest is 10.22.12. And it's available from the GeoDa Center site. You don't have to download it. Nothing has changed in terms of functionality. The only thing that we changed is the two data sets were cleaned up so that we didn't talk about this one yet, but the Italy banks data set, which we're going to be using next week, was missing a variable, and that it now has the variable. And then the Chicago community areas now has the total population in the 2 years as well.
Okay,
but
so
no updates doesn't work.
okay, so I'll make sure next week to update my version. I'm 2 out of 3 outdated with my version of GeoDa, but next week I'll update again. All right, one good thing about GeoDa, since we're using this Gary data, is that it's part of the sample data, as Luke just said. So we can just come straight to sample data and find it here. See, Gary. So just by double clicking here, oops, we already get it. So we get the themeless map with the regions in France.
These are départements. There were originally 86, but Corsica was removed. So we have 85 in the mainland. Corsica is an island. I know you guys didn't do geography of Europe.
Okay. So we can find PCA under clusters. Okay, so menu clusters, PCA. And then it's just a matter of choosing the variable. So I'll hold shift and arrow down until I go all the way from crimes against persons to suicides. To replicate exactly what we did in the notebook, let's change the method from singular value decomposition to eigenvalue. And then we keep standardized. And we hit run. And from this, you can see that basically we got the same. Everything is on the slides, right? So the eigenvalues, 3 principal components with eigenvalues greater than 1. They are sorted differently from the notebook. I'll update the notebook. So 3 greater than 1, the loadings. I mean, of course, I won't repeat the interpretation that we can do from these loadings. So everything is showed here. What we can do is choose how many, after we choose how many components we want to retain, we can come back to this tab here on the output and say, let's say only 2 components, if that's all we want. Or if we follow, let's do 3, just for consistency with the Kaiser criterion. And with all the interpretation I told you about the script plot and all of that. So if we choose 3 components, we hit save. And GeoDa will prompt us to select names. So if you can label them already, awesome job. You can just do it here. If not, just keep it PC1, 2, 3. Okay. If we go to the attributes table, you'll see that the 3 components, the scores will be there. So the new variables are all there, right? And with their values, which allows us to come to map, box map with a range 1.5. And we can go all the way to the bottom, find PC1. So menu map, box map, I'm choosing 1.5 for hinge, PC1. And we get the very same thing that we had before, right? Okay. But what GeoDa allows us to do is to, oops, sorry. I'll use this one here. So we can click on this button. I think it's on Explore if you want. Yeah, Explore Parallel Coordinate Plot, or you can just use this button here with the lines. And again, choose the 6 variables that we're using for our analysis. So I won't just do the 4 as Luke did in the slides, just so we can see the difference. Anyone needs me to wait? Y'all good? I'm seeing heads shaking like this, so I'm just moving forward. And from here, we can just choose any category that we have in our box map and see how it relates to the actual variables, right? So for example, we have these regions. They are not like a significant cluster. We're not doing the local Moran's eye here, right? We're just seeing the box map. So we're just seeing the lowest, yeah, we don't have any outlier. So we just see the first quartile here. So this is showing the regions that are in the first quartile of the variable. And then we can see from here how their variables show, right? And see how similar they are. So they do show low values for the variables crime against persons, but not that much because this variable was not did not have a large loading on the first component. That's why we don't have much similarity for it. But for crimes against properties, then we have a lot of similarity. And we see that low values for PC1 imply low values for crimes against properties for the variable, right? Which means high crime, yeah, high crime rate, right? So that's why this is a region with low morals, right?
The other thing you can focus on is, so all these lines represent an observation in higher dimensional attribute space. What you can see as the ones that squeeze together and where they squeeze together, like in the crime against property and in the donations, there's a group of them that squeezes together, and those are more clustered in multivariate space than some of these other ones. You know, a quartile is a lot, it's a quarter of the observations. So some of these are more clustered than others. And if you have a good visual memory, you may remember that the high cluster location of the local moraine was up there, but it was a subset of this region. And those would tend to be the lines that squeeze together most.
I mean, we can actually do that, right? We still have time. So let's just create a weights matrix pretty quickly. If Zoom allows me to. There any way to here, weights manager. So I went to tools and weights manager. I'll create a contiguity matrix. So for ID variable, I'll just use this code. Queen first order. I mean, as simple as it gets. So create.
It doesn't get simple because you're using a sample data set. So you need to save the weights file to your desktop or something.
Okay, I'm saving it to downloads. Right? And now space univariate Moranzi, local Moranzi, sorry. And PC1 with these weights. And here it is. Right? So as Luke said, it's inverted. The signs were different from what we had in the slides, but it's the same as we got in the notebook. So now we can actually use the statistical significance for the clusters that we get here. And if we hit on low, you see that you get values that are more similar, especially here in the variables that were more important for PC1. So infants, suicides, donations were not important, literacy, crimes against properties. And if we click on the high cluster, yeah, now the variability is a bit like all the way, but it's the combination of the PC1 that actually mattered for these to be considered a cluster. So it's basically what we said before. We can tell that each of these regions have low literacy, high value for the variable infants or suicides or any of these. What we can say is that the combination of these variables resulted in a high value for PC1. So in this case, for high morals, for the analysis, and then if that is the idea, they show similar values in this multivariate space. Whereas it was because they had high values for like 2 or 3 out of the 4 variables that were important, then in the end, it will be the same because we're combining this and simplifying our results in order to highlight the spatial agglomeration that we get in this multivariate space. Does it make sense? Any more questions, comments? I think this is all, right, Luke? Anything else we're missing? I mean, if you allow, Luke, we'll stay here for 3 more hours loading more windows and more the different analysis and linking them all. Okay, so this is it. Now